All right, hello guys. This is Costa. Welcome everyone to join our monthly development meeting for conservative Q learning. So to give you a little intro, this is a meeting that we host every week for our library ClingRL. So for each month, we try to pick out an algorithm that we're interested in and try to reproduce it. So over here, you can see the Slack channel to join our discussion, and you can click on this link to check out future event invites, as well as this link to check out previous recorded videos. The topic of our weekly meeting today is conservative Q learning for offline reinforcement learning. It holds a lot of promise for applying reinforcement learning to a lot of real-world challenges where obtaining real-world data is prohibitively expensive. So that will be the topic that we'll be focusing on. So before we start, maybe someone can give we can have a short discussion on how everyone feel about the paper. To any thoughts or comments. So maybe let's start with Nicola. What do you think of the paper, and any comments and thoughts?
Yes, well, I haven't got down to reading it, so I'll just spectate this meeting most of the time.
I gotcha. It can definitely be difficult to read.
Yes.
What about you, Roslyn?
For me, I kind of managed to get the first pass in.
Mm-hmm.
And as you said, well, maybe not necessarily as you said, but the point is that there is a data already available, like reward and all that kind of stuff. But what they try to address is kind of the accuracy of the updates we are doing, be it a TD, for example, when updating the critic value.
Okay.
And based on the data, they propose a method to compute a more, not overly optimistic, but neither overly pessimistic target value, basically. Hence the lower bounded, I think, critic. Lower bounding the Q function.
Yes.
I think there is a similar term. So that's probably the core of the paper around page 4, equation 3. But I still have to properly understand how they're doing the computation.
Okay.
Because there seems to be, they add like different policies to sample the data from to get the different Q value samples. To use it to average, so there is a kind of there's quite a bit going on.
Yeah, for sure.
But beside that, well, so basically, once you have you manage to update the critic well enough, stably enough, but that's where all the other benefits stem from. In this method.
I see. Yeah, that's a very good summary of what's going on in the paper. All right, let's maybe move on, and I'll do sort of a short presentation on it. So the presentation is, for the most part, I just kind of put kind of screenshots, try to basically highlight things that I put, try to basically highlight the things that when I read the paper. So I haven't changed this page, so don't worry about it. So the problem that the CQL is trying to address is how to apply offline reinforcement learning to offline data. Basically, there is this problem of distributional shifts. So this is directly from the paper. In principle, it is possible to leverage offline RL algorithms by using large dataset, but in practice, fully offline RL methods pose major technical difficulties stemming from distributional shift between policy that collected the data and the learned policy. So basically, it's saying the learned policy, let's say from the Q function, because the Q function is different different from, let's say, an optimal Q function, the policy that derives from it, which uses an argmax operator, it's going to be different from the policy that are used to collect the data. So the authors suggest this has made the results fall short of full promise of such methods. And the main challenge that they're trying to address is due to issues with bootstrapping from auto-distribution actions and overfitting, this typically manifests as erroneously optimistic value function estimates. So this sentence might read a little strange, not exactly know what's going on, but we'll show you later what that means, at least I think. So overall, the paper, in theory, they aim to address the limitation by learning a conservative Q function such that the expected value of a policy under this Q function lower bounds its true value. And then in practice, CQL augments a standard Bellman error objective with a simple Q-value regularizer, which is straightforward to implement on top of existing DQN and actor critic implementations. So in practice, they suggest that it only takes about 20 lines of code to incorporate CQL, which we'll also see in the presentation. So here, let's truly understand what this auto-distribution action means. So over here, you have this is a standard Bellman. This is a standard Bellman error objective, which is to minimize the Q value as well as the Q value of the next state and the next action plus the reward of the current state and the current action. So if you read about the DQN implementation, this is a standard DQN update. So the authors basically suggest that this yellow part, which is a target for the Bellman backups, or for the Q function, this yellow part uses actions sampled from the learned policy. So this A prime is sampled from the learned policy that uses probably an argmax. However, if you look at the pink part, the Q function is trained only on an action sampled from the behavior policy that produces the data set. So it's saying over here, the actions are sampled from the behavior policy that is different from the policy that sampled this action A prime. So that is what the authors is trying to say. Any questions for this part?
So maybe at the cost of repeating what you've said, the QSA in the pink highlight was the SA pair was sampled using a different policy, the behavior one, by beta. But when we try to do the update, we are calling our estimate Q hat function on S prime and A prime. Oh, wait. I am reading from your slides.
Sorry.
We have S prime, A prime, which comes from, well, the S prime maybe was also sampled using pi beta.
S prime.
It's the next state, so it comes with SA basically.
Oh, yeah. The S prime is the comes with the data set, yeah.
So the distribution shift comes from using a different pi hat k to get the A prime.
Yes.
Which in turn makes us query the Q value of the S prime somewhere where we do not necessarily understand like the real Q value because we never went there before with pi beta.
Yes. So I'm trying to make some connection with the code. Yeah, there's really no good ways to do this. But when you read the code, right, you basically try to find out which Q values that the action A prime has the biggest value on. And then you select it. So it's saying because when you do this process, it's using the learned Q values, that is different from the Q value that is trained only on action sample from the behavior policy. So there's this disconnect here.
I get the idea. Thanks.
Yeah, my pleasure. Sorry for switching off the. I thought it wouldn't affect. So for the conservative off-policy evaluation, so their main idea is to, first of all, let's bound the Q values. So over here, we have the standard sort of Q update for DQN. The author suggests, first of all, we want to find the Q values, find the Q from this family of Q functions, find this Q such that this Q value is minimized. So it's over here, and plus this standard DQN update. So the first step is to sort of minimize the Q value, and then it's for some state action pairs. This is called a mu SA, which we don't know what they are at this moment. And then the next step is to say, okay, so this is maybe too pessimistic. So after we make the Q value as small as we can, we're also trying to maximize the Q values. But in this time, we're trying to maximize the Q values based on the data sampled from using the data sample from the data set. So over here, this looks like a minimization on the Q value, and over here we have a maximization of the Q value because you have a minus over here. So this part is being minimized, and then because of this plus sign, this part is minimized as well, but because of this negative sign, this part is maximized.
Okay, quick question.
Yeah.
I see we suddenly transition from pi beta as the behavior policy to pi hat beta.
Mm-hmm.
Do you have any idea what motivated to change?
Not exactly.
I am looking in the paper right now.
Mm-hmm.
It just suddenly appears, kind of.
Oh, really? There's no previous reference of it?
I don't see the definition.
Well, I do notice there might be some typos, right? For example, over here, you have the pi hat beta left parentheses, but the right parentheses is a little off.
Okay, so it was earlier. Okay, in that case, yes.
I don't know. Maybe it's a typo, but I'm not really sure. So this, yeah, you're right. Over here,
It's defined. It's defined.
Where is it?
Just where you highlighted the typo. That's actually where they defined it. Pi hat beta. It's a form
I see.
of softmax over all the data sets.
Oh, actually, yeah.
The empirical distribution, empirical behavior policy.
Yeah, and I have a hard time understanding their significance as well. But
well, I guess pi beta is the theoretical policy if we could sample ad nauseum, but the pi hat beta is ultimately what we get from the data set we have sampled using pi beta.
Mm-hmm. Yeah.
So I guess they wanted to make the distinction.
I see. Okay. Yeah. So continuing on, I think sort of the takeaway is they're trying to maximize the Q values based on the data set, but minimize the Q values based on some data that we don't know what this mu is yet. But the authors are saying if we just set the mu to just pi, then there's some interesting properties. And overall, they sort of this is kind of theoretical, and over here is how they make it a little more general. So they have this form where, again, they're trying to maximize this Q function given some mu, and then they're trying to minimize they're trying to minimize this Q function given some mu and try to maximize this Q function given the data set, and then they have the standard Bellman error. And then lastly, they have this sort of a regularizer R of mu. So equation 3 should be basically kind of equivalent to equation 2. But this is what the authors called a family of optimization problems over this mu that we don't know quite what they are yet. So in practice, this is kind of what they come up with. So they replace this mu term with this log of sum of exponential of the Q functions, which if you just look at it, it's very unintuitive as to what it's doing. But if you see this highlight over here, so it's saying this term, I think the intuition is that corresponds to a soft maximum of Q values at any states S, given rise, basically a soft maximum of Q values at any state. But it's also not exactly clear what the soft maximum is. I think it probably has something to do with the soft Q values.
It actually seems quite similar to that notion from the SAC, right?
Yeah,
from the Q value, we try to derive the implicit policy it induces by taking the softmax over all the support, all the data range.
Yeah, they probably have really good reasons to do so, but I don't quite see where the intuition is coming from, but this is kind of their sort of practical algorithm choice. You still have the Q value update, but you're trying to maximize the Q values with respect to the data and try to minimize this soft maximum of Q values.
But this is ultimately the part that is sampled using mu A given S, like a unknown distribution over action.
Yeah, I don't know where this mu part went. They basically explained it if we let this regularizer be the KL divergence against a prior distribution.
Since okay. Gotcha.
Yeah, they somehow replace it, but I'm not exactly sure. Not sure about the maths behind them. But this is eventually what came out, and yeah, what else? And then basically we have the results. The authors further include a lot of theoretical analysis, but I didn't read them because I'm not really getting anything from them because I'm not really that theory oriented. So I just kind of skip these safe improvement guarantees, etc. I just kind of look at this practical algorithm and the implementation details. So apparently what they do is to basically replace the Q-learning update, the standard DQN learning updates with this sort of CQL objective. And if you're using the sort of actor critic style, which is either the SAC or deterministic policy gradient, and then they also have to update the policy with this term. So that is kind of everything that I got from the paper, and they got very impressive empirical results as well.
But this is still... Oh wait, they even have SAC as a baseline.
Yeah, so I think this SAC is probably... I don't know, is this SAC just running it directly without any offline RL modification?
probably.
Okay.
Or maybe even on the real task. Now I'm kind of curious, where did they get the optimal trajectory that are in the dataset?
Yeah, so when I was watching the Sergey Levine's video, he actually talks about the dataset shouldn't be generated from like an optimal policy because it has a bunch of assumptions and which is not.
I think he said it does not necessarily need to be from an optimal policy.
Right, exactly. And for example, over here, not for example, and furthermore, they have some impressive results on Atari games as well. But using different data, like for example, over here, they're using 1% of sort of the best data, and they're able to achieve really good results. And using
human for Atari.
I don't know exactly, but probably.
Okay.
Yeah, and if they're only using 20% of the data, which is the charts that are shown over here, then the results is more unstable, but still good, I guess. But yeah, this is kind of what I got from this paper for now. And I think the next step would be probably we should dig into the code and see what is actually happening, because the authors suggest that this could be easily incorporated to existing algorithms, but we'll have to see. And another thing is, so they implemented with SAC and quantile regression DQN. So something that I was wondering is, what would the performance be if they implemented on, let's say, DDPG or just a regular DQN? Because they're more accessible in a way because they can be easily coded versus SAC and quantile regression DQN. There's a lot more sort of details related to these algorithms.
I guess we will find out.
Yeah, for sure. So I'm very looking forward to checking out the code and giving it a little try with the offline RL algorithms.
Well, I managed to get a look at the part where they said they add CQL to SAC.
Okay.
And it actually seems quite easy, but maybe not easy, but quite simple.
Okay, great.
As you have presented before, there's just here the mu becomes a kind of a uniform distribution. Yes. And well, basically they sample a lot of action and query the Q value on that part, and then they minimize it, as they say, to lower bound it. And then the rest is just like standard updates.
I see. Okay.
It's really not that complicated.
I see. That is very interesting. Yeah. So I very much thanks for taking a look so early on. I would very also look forward to trying this out.
Are there any? Maybe try to look up CQL in that DQN. I'm not sure.
Yeah, I don't think
does that seem to be. That only looks like the network structure.
Yeah, in the SAC code, you see the CQL.
Yes, explicitly.
Yeah, that is probably not the case right now for DQN. They have DDPG. Yeah, it's not over here. They only implemented it for SAC, I think.
For the Atari, I think if you go back to the root of the repository, there should be the Atari, yes. And there maybe, probably Batch RL then.
Yeah, I remember somewhere over here they have this Quantile agent, and
Quantile.
eventually, they.
But this is only the structure, it seems. The algorithm logic is kind of somewhere else.
Yeah.
I think it said in the README of the original repository. In the README, they say, okay, here
It's
is
over
the
here.
discrete version.
It's over here.
Oh, wait a second. Did you get it? Ah, nice. Which one is it? Quantile agent.
Yeah, it's a multi-head, a batch RL multi-head Quantile agent.
I see. Oh, yes, there is the log sum XP that is back. Line 228, I think, or 29.
Uh-huh. Yeah, so I would be, for the implementation week, Rosalind, would you be interested maybe looking at the SAC part of the code, which I know you're more familiar. Maybe I can take a look at this DQM part of the code.
I will start with SAC and continuous environment in general, let's say.
Okay, sounds great, and I can definitely take a look at this DQN parts. And if you find anything, please feel free to post it in the Slack chat. And
Okay.
And Niju and Nicola, I don't. So for the implementation week, feel free to try it out. Play around the code, and if any questions or comments, feel free to post in the Slack channel as well.
Yeah, sure.
Don't feel obligated. Just if you guys want to give it a try.
Yeah, so I'm not that much sure about SAC, but I'll give it a go on DQN to my best.
Yeah. Sounds good.
In between, I found another implementation somewhere in that. I'm just sharing it in the chat, but I'm not sure whether this is a very perfect implementation or not.
Okay, let's take a look. This is someone else's implementation, offline RL. I haven't seen this repo before. Thanks for referencing that. I think it's going to be really helpful. Soft.
Easy
Yeah,
to
hopefully.
TensorFlow too. Nice.
Yeah, this is also with a different repository. This is with Acme, I think.
Acme, was it a DeepMind?
Yeah, it's DeepMind. This is DeepMind's repo.
Damn. There are so many frameworks now. It's
Yeah.
hard to keep track. RL kit, batch RL, clean RL, baseline, stable baseline free, Acme. What else?
It's all for
Yeah,
different
I think
research.
it's kind of a
RL Zoo.
everyone develops
Dopamine.
frameworks.
Yeah, all for different purposes. I think in
Yes.
I think in ClearOwl, we just try to be as simple as possible with the code, everything in one place, and when you just download the code, you just hit run, and it can run. There's no installing a bunch of things, which they're definitely helpful in a lot of situations, but we just try to make
You
the
make
code.
it sound like noob RL.
Yeah. New RL. I love it. But yeah, this is a very good materials. Let me post that over here as well.
Yay.
So over here as well, I want to just sort of for sanity's sake to know where things are. I think it's very nice. Okay, yeah. Other than that, I don't have any more things prepared for CQL. It's a very difficult paper, so just yeah. There's not much else I can go for it. Does anyone have any thoughts or comments?
Overall, I will say the code will probably give us a better intuition.
Mm-hmm.
Actually, I have to first see the code before understanding more or less the equation tree. So
Yeah, for
maybe
sure.
it's my bias, but
I agree. And also, in the newest accepted list of NeurIPS papers, I think there's a lot of new things as well. NeurIPS offline RL. Yeah, I don't know where it is, but it's somewhere. I saw it somewhere. How do I even search? Okay. Can I search for offline? Oh, okay. So CQL is actually presented in NeurIPS as well.
indeed.
And you have MLPL, model-based offline policy optimization, and you have MOR. Oh, that's really funny. Did you see that?
It's basically the same thing.
Yeah. That's really interesting. Their title just kind of clashed. You don't see that very often. Okay, let's keep shopping. And expert supervised reinforcement learning for offline imitation learning with
Misspecified simulator. What does that even mean?
Yeah, this is also interesting because the first author has the same first name as I do. So for this sake, I'll check it out real quick.
Solidarity.
Yeah, I know, right? Oh, this is so strange. And my last name is only 2 letters away.
Maybe you have an alter ego. When you sleep, you become Shenyi Jian.
Yeah, I don't know. Oh, this
Like
is also interesting.
Jekyll and Hyde.
This is also interesting because it seems this is the Boston Robotics kind of robot. See that?
Spot Mini?
Yeah, I don't know.
Misspecified environment. That's what
But the
got
name,
my attention.
yeah, the name is very strange. Misspecified.
How do you misspecify an environment?
Yeah, what does that even mean? In any case, there's a lot of stuff going on, and there's also even a offline reinforcement learning workshop. So I think there's probably going to be quite a lot of research that will go on in this field. I see. But yeah, super interesting. Well, we should probably try to make. Yeah, if you're registered to NeurIPS, you should probably try to make it. All right. I don't have anything else prepared.
Apparently, the misspecified refers to having the simulator, well, basically a wrong simulator. For example, when compared to real world.
Oh, I see. Then they could have just said with imperfect simulator instead of misspecified.
Well,
yeah.
had they said it, we would probably not have checked their paper. So
Yeah, I don't know.
you gotta give them that.
Well, I would check it just because of the first name, but yeah. In any case, this is definitely interesting stuff. Looking forward to checking out, especially what the communities think are the best papers and so on. All right. Does anyone have any more questions or comments?
I'm alright. Thanks for the presentation. Kind of got a better perspective on some part of the algorithm.
Oh, I'm glad you find it
Especially
helpful.
that pi beta. Now I know. Finally.
Okay. Nice.
I'm good here too. I joined a bit late. I thought the timing is same as the previous last week. And, suddenly I saw this thing Slack channel and then I joined.
No worries. Yeah. Well.
I didn't follow the presentation.
I see. Yeah. No.
I think we all have different time zones here. So.
Yeah, I think it may be helpful if we try to consider moving this meeting time to, let's say, Saturday as well. But I don't know. We'll see. All right. Thanks everyone for making it. If there's no any more questions or comments, we should probably end the meeting early. Thanks everyone for joining, and hope you have a good weekend.
Likewise.
Thank you. Thanks everyone. Have a nice weekend. Bye-bye.
Yeah, thank you. All right, see you everyone.
See you.
See you.
Bye.
Bye.